of the chassis. So when you taught that lecture on beams and shells, that helped a lot.
Nice.
So I used beams to model the chassis, and then I was able to get a decent result. And I actually did a convergence study too.
Nice.
Yeah.
Nice. That's awesome.
But I gotta redo that.
Oh.
Because it was giving me all sorts of errors and stuff in Ansel, so
I see.
I wasn't super confident that my results were that accurate.
I see.
Great.
Good.
Hey. Oh, it's good. You guys are in a much better mood than mine. I got your all my undergrads still kind of semester. So you guys are doing good. What would you say that? Yeah, it's semester. I know it's December now. It's like December, so this week, next week.
Hi, Dr. Tran.
Hey, Jasmine. How's it going?
Could you hear me? Like, just was my voice like?
I heard something in the background. This is the first I heard your voice, though.
It was only my voice, or just like hearing like a video or something playing?
There was a video playing.
It was yourself, yours.
That's what I thought. I'm like, it sounds like me, but I don't think I'm talking right now. So I'm wondering where.
Yeah, sorry. Just yeah.
How was your weekend, Professor?
It was good. Yeah, I watched this new series on Netflix called Arcane. It's based on like League of Legends.
Yeah, I've been hearing about that. It's on the rage.
I honestly I wasn't that high on it because I thought, to me it looked like, they're just trying to cash in on the League of Legends game, but it's actually really good. And so my friends kind of forced me to watch it because I was hanging out with them and they really wanted to watch it, and so I kind of had no choice. But we watched it and I liked it. It was really good.
Yeah, that's cool. I've still yet to watch it myself.
How was your weekend?
All right, just busy studying.
One more week till Thanksgiving. And I know this is I'm sure it's a really busy week because I know every professor is probably like me. We just try to cram everything in the last minute.
Yeah, not much of a Thanksgiving break if
Mhm.
I got more studying to work on.
Mhm.
For the last word problem, I was able to correct that. I found a mistake there, but I guess you had to answer slightly off on what was wrong. And those all really similar to yours, so I actually copied it as well to do the MATLAB. I got the same
Uh-huh.
answer.
Oh, the final answer. Oh,
Yes.
oh, it's probably just a rounding. I mean, I'm mostly just looking at this. I think something like this probably is because this factor up there
Uh-huh.
is a little bit off, or something over here is a little bit off. So
Okay, because it's weird. I did the same. The copy of yours is exactly as it is.
yeah.
I got the same answer though.
Uh-huh. Wait.
So I did mine first.
Yeah.
Got this.
Yeah.
Did yours or what you had on here?
Yeah.
I got the same answer as this.
Uh-huh. Yeah, I
It's
think
kinda weird.
because I think there's some rounding things because
Uh-huh.
I don't think I put like full precision on this, or maybe I do
Oh,
put full
okay.
precision. So like something if it's just off like that, it's probably just rounding. So
Oh, okay.
yeah,
I see.
I wouldn't worry about it.
Okay, cool.
That was me, Dr. Joe.
Oh, is it? I say I just checked it right now. The Discord thing has been so interesting because you guys all use your usernames like me too, and so like people message me and then I answer the questions. I'm like, I don't know who that was.
All you gotta remember is the logo.
I see.
It's the logo.
And like sometimes like multiple semesters will pass and like I still don't know who are messaging on Discord. The difficult thing is when people send me their work over Discord and they don't have the names in their work, and I'm like, who should I send this grade to?
Have you got to any Nigerians scams over Discord yet?
Wait, say again?
Have you got to any Nigerian scams over Discord yet?
Not yet, not over Discord, but over Gmail a lot. Yeah. One that's popular nowadays is that scammers will take an email that looks very similar to like your boss's email, and so I don't know how they get this information, but they got Dr. No's name and they create an email that looks very similar to his email, but like with just one letter off at Gmail. And then he asked me to like, or the scammer asked me if I could buy him some gift cards, some Target gift cards, and then send it over to him. And so I almost fell. I mean, I didn't fall for it, but I responded to one. I responded to one on the first. I'm like gift cards. I'm like, why do you need gift cards? So at first they'll be like, they'll just send an email say, are you free right now? And I said, yeah, I'm free. It's like, can you buy me some gift cards? I'm like, what do you need gift cards for? And then they don't respond. I'm like, okay, that's probably a scam. I probably shouldn't talk to these people.
Yeah, you should try to mess around with them more.
I've seen videos of people doing that on YouTube, and it's great. I love watching those. It's yeah, but I don't have that kind of time to mess with them. I'm
Just
thankful. Oh, go ahead.
hyperlink one of your lectures to them so that so like here's the gift cards just next to your lecture.
Yeah. I'm look forward to the day when, like, you know, when all of our generation kind of gets old enough so that, you know, these scams don't work. Because I feel like most of the people that fall for these are like older people, just because, you know, they don't really know, they don't know any better. The midterm won't have an 8x8. It does not, but it has 7x7s. So it has one off from that. It's hard because, you know, with the you know, if you have anything less than if you have anything less than 3 elements, then it becomes a little bit too easy. And so, you know, there's 3 elements each for those problems, but they don't get up to 8x8s, but they can, but they'll be 7x7s. But no more than 3 elements. And so, you know, there's that for you. Yeah, so it's just gonna be the setup, and so you don't have to solve anything, because you're not gonna have you'll have a calculator, but you won't have MATLAB in front of you. So I just want you guys to set it up.
So no
Okay.
cheat sheet and all that.
Yeah, cheat sheet and everything. Yeah, we'll talk about it today. Yeah. Okay, it's 5:30, so let's go ahead and get started. All right. All right, so good afternoon, everyone. How's everyone doing today? Good. All right, another question. So since we only expect to set the matrices, yeah, so there's going to be no questions on reaction forces and stresses. And so, you know, I just want you to do the setup. And so just element stiffness matrices, assembly, and then apply the boundary conditions. And then that's basically all 3 of the problems right there. It's just they're all going to be different settings. But yeah, there's no reaction forces and no stresses that are going to be on the midterm. Yeah. All right, and so we are on Tuesday of week 13, so the week before Thanksgiving. And so, you know, I know this is a really busy week for everyone. So, you know, I appreciate everyone coming here to the lectures because, you know, and not, and, you know, I don't take attendance or anything, but, you know, I'm, you know, contractually and legally required to be here. So it's always nice to have, you know, more students in the class than not. So, so thank you guys for always coming to the lecture. Okay, and on Thursday, you know, I will see all of you in class because Thursday is our midterm exam. And that's going to take place in person, right? And so just to kind of remind you on what you can bring for the exam is that it'll be you know, a 75-minute exam, so it's just going to take place during the lecture. You're allowed to bring writing utensils, so pencil, pen, whatever you want. You're going to bring a calculator. Okay, that should help. That should help with some of the calculations that you have to do. And you can also bring a cheat sheet or a sheet of notes. Okay. Right, and the cheat sheet's going to be 8.5 by 11 sheet of paper. Okay, and you can use both sides. Yes. So you can type it, you can write it, you know, whatever you like. You know, just make sure that you can read it during the exam. Okay. And I always tell people that, you know, I think there's one strategy with cheat sheets like this where you try to cram as much information as you can on them. You know, you can print all of the homework solutions, all the lecture notes, and cram that in there. And that's certainly one strategy. But I think the better strategy to go with is to you know, kind of take your time and really use the cheat sheet or putting together your cheat sheet as your means of studying for the exam. Okay, because, you know, when you have to kind of take you know, several weeks worth of information and then put it onto just one sheet of paper, your brain is actually naturally kind of filtering out, you know, what's most important and organizing the information in your head into a way that you can kind of quickly pull from it on the test. And so, you know, just the act of putting together your cheat sheet and, you know, organizing information and writing the notes for it, I always find that that's a really great study tool. More so than, you know, just trying to cram everything you can on there and trying to, you know, rely on that on the exam. Because what I've noticed is that, you know, for those people that try to do that, you know, you kind of spend more time on the exam kind of looking through your cheat sheet, trying to find, you know, exactly where the right answer is, more so than doing the exam. And so, you know, this and so the whole idea kind of that whole, you know, lesson to me kind of got hammered in when I took a programming class in grad school. and they actually let us bring our laptops to the exam room. I mean, they put like a blocker in the room so you can't access the internet, but you were able to open up like MATLAB and Python in that case, and actually write code and test it for a programming test where you have to write code on the test. So everyone's like, wow, this is going to be easy, no problem. The average on that exam was 35% out of 100. So, and the reason was because everyone spent the entire exam just trying to type code into their laptop and run it, more so than just taking the exam itself. And so, no one finished. And the questions that they did finish, they were not worth that many points. And so, it was a very hard lesson, I think, for everyone in that group. And so, I've been sharing that story lately just to kind of, tell you not to do that. I think especially because, I think for a lot of you, this will be your first time or one of your first times doing the exam in person. And so, we all kind of have to learn how to take the exams again. So, I tell that story just to kind of, help guide your stuff. Okay. All right. I posted the homework solutions. And so the homework solutions, I apologize. So I meant to post that on Friday when it was due, but I kind of forgot. And so I posted that on Monday first thing. Okay. So that's available for you on Canvas. And so I believe I sent an announcement about that. And you can find the file on Canvas as well. Okay. Seating. So I think there won't be enough seats in here for there to be one seat in between people. And so it'll just be just come in and sit down. So there's don't worry too much about the seating. I mean, of course, try to keep as much distance as you can. But I think we're gonna have most of the seats in here filled up. Room number. So it's going to be in CS 309, and so it's our usual lecture room. Yeah. Yeah. Okay. And I think that's the announcement. So the due date for ANSYS activity 5 that's been pushed back until after the break. So just to give you guys a little bit more time for that. And then when we come back from the break, we're going to have one more ANSYS activity. And so that's kind of the plan for the for this week and the week after the break. Okay. Oh, your proposals. So I was able to look at your proposals today, and so I gave everyone feedback. And so definitely take a look at those comments. And so overall, just like I said last week, everyone thought up some really good projects. So I'm really looking forward to to looking at the results. Okay. And if you weren't able to turn in the proposal, then please do so. I can still give you late credit for it. But more importantly, I want to be able to see what you have planned for the final project and to give you some feedback. Just to make sure everyone's kind of on a good path, because I don't want to get to like the very last week of class or even finals week, and then you guys are struggling to find what a good project is. So I want everyone to kind of get that settled right now and to get some feedback from me, just so that everyone can kind of start off on the right foot. Okay. All right. Question.
For conception part of the midterm, will be more directed more towards the stiffness method, or will be answers as a whole, like meshing elements and boundaries?
Yeah. So the question was, for the conceptual part of the exam, is it going to be based on just the direct stiffness, or is it going to be on everything that we covered? So it'll be just on direct stiffness stuff, and so it'll be just on that, I think 3 or 4 week period where we just did direct stiffness. So everything else, all the ANSYS stuff, I'm gonna, the way I'm gonna assess you on that was, first of all, the midterm project was part of that, and also the final project. So this midterm exam is just on direct stiffness. Yeah. Yeah.
Kind of like to go off of that, will it be the conceptual portion kind of similar to the homework?
Yep.
Questions?
Yep. So there'll be short answer questions, and so and there's only two, I believe. Yeah, there's only 2, and so basically I'm going to ask you a question and you'll answer it in like 3 or 4 sentences.
And in terms of like the material for it, you covered that in the video?
Yes. Yeah. So the review video, I did just a little bit of everything in that video. And so if you kind of start with that video, it's only an hour long, so it doesn't cover everything in a lot of detail, but it'll at least give you a sense of the scope of what's on the exam. Yeah.
And so kind of like 2D or 1D is up for game.
Yeah.
And
Yeah. 1D and 2D.
the trusses, the springs, and the beat.
Yep. Mm-hmm. Yep.
And how about because I know we didn't go too much for like the reaction forces or like the stresses for the beams. Will we cover that?
No, so the exam won't have any of those because I can't ask you guys to solve any of the systems on the exam because it's going to be closed computer. And so basically all three of the problem solving questions are going to be, give me the element stiffness matrices, assemble it together into one big system, and then apply the boundary conditions. And then that's it. So all three problems are going to be exactly like that. Yeah. Mhm. All right, and so I think that's all the announcements. So are there any other questions I can answer before we get started? Okay, all right, so let's go ahead and start. All right, so for today, we have just kind of one lecture kind of in an awkward place. And so what I thought to cover was what's known as verification and validation. Okay, so it's a little bit of a unique topic in finite elements. And I will admit it's not often covered in a lot of introductory classes, but I think it's extremely important. And sometimes in the business, you'll hear people refer to it as V and V. Okay, and so when you hear the terms V and V, this is kind of what they mean. Okay, all right. And so to start, let me just start by making a general comment that throughout this entire class, we've seen that finite element simulations can be a really powerful tool for engineering analysis, right? Okay. Because we've seen, finite element simulations used to, predict things like deformations, predict things like stresses, okay? Things that normally would be really hard to compute otherwise, either with an analytical equation or through some kind of physical test, right? And so finite elements kind of gives us a way to kind of really leverage the power of computers to, assist in our engineering work. And, if just to make a personal comment too, that, I think as computers get more and more powerful, the capabilities for finite elements is only going to keep growing and growing, okay? And so, I think it's, first, of course, I think it's great you guys are all taking the class because, I think it's going to be a really important skill to know, going forward, okay? All right. But as powerful as finite elements is, it's always important to remember that it's only an approximation. Okay, it's not truth, right? It's not it's not a what's called a crystal ball that can see into the future, right? It's only an approximation. Okay. Okay. And so we want this to be like a good approximation for reality, but we have to remember that it's not always that, right? Because the results that we see and the data that we see from finite elements, they're always based on the governing equations, right? And so underneath the hood for finite elements, we have our differential equations that we're solving, and we're solving that using a numerical method, okay? And so a lot of the work that we do in finite elements is based on just basically the assumption that these equations that we're solving and the way that we're solving them provides a good approximation, okay? And so to kind of put this in another perspective, what we can say is that finite elements is only a model for reality. It's not reality itself. And I underlined the word model there because model is kind of a key word that's used to describe a lot of different things. Okay. But for our context, we can give model a specific definition. Okay. And so when we say model, what we basically mean is something that can give you a prediction of reality without actually, measuring it. Okay. And so that's a very, very, very broad definition because there's a lot of things that can predict what reality would look like. Okay. And so, of course, there's different classifications for models too. And we're not going to go over the full spectrum, but I will tell you what finite elements is. Okay. And so finite elements kind of fits within a category known as a mathematical model. And the reason we call it a mathematical model is that we basically use equations and we use numbers and we use computations in order to form our prediction. Okay. Okay. All right. And so with being a model, and so the fact that finite elements is only a prediction, there's a lot of limitations on what it can and can't do. Okay. And that's really important to note because it's always important to know what your limitations are for the tools that you're using, okay, and how you can make those tools as useful to you as possible. Okay. Because there's a common saying in the world of computational engineering to say that there's so many different models out there that could predict all different manners of things, but no matter what model that you have, they're all going to be wrong. Okay, and so the saying goes, all models are wrong, but some are useful. Okay. And so what that basically means is that no matter how well you set up your finite element simulation, it's never going to be a perfect representation of reality, right? Which sounds kind of bad, especially at this point in the semester, right? And so to say that everything we've been doing in this semester is wrong, that's not it at all, right? And so what I mean by that is, if you have a physical situation, and so let's say that you have a, let's say really simple, let's say you have a cantilever beam, right? And you're applying a force on that beam, okay? If you told me that your finite element simulation of the cantilever beam can predict the deformation up until like the 10,000th decimal, right? Not even that far, maybe up to just the 4th decimal, right? I kind of be skeptical of you, right? And so maybe we can say that we can estimate the deformations up to the 1st or 2nd decimal, but as you get more and more, that becomes hard to really justify. And so and so in that sense, the finite element simulation is not exactly the same as reality, but it's still useful for us in order to perform some of our work. Okay. All right. Any questions on this so far? Okay.
Yeah. Just
Oh,
kind of like, so in that case, that's why we would have like safety factors and
Yep.
have like better approximate that or.
Definitely. Yep. Yep. And so even when you're doing especially when you're doing hand calculations and simulations, and so you have to account for the fact that, whatever you're using to predict, what's going to happen in reality, you have to account for the fact that there might be some error in those calculations. That's exactly right. Right, and so to kind of further illustrate this this notion of a model, let's actually look at that that case, right? And so if we have a cantilever beam, okay, and so we have a beam that's fixed to a wall, and let's say that we provide a downward force F, okay? Right. And so if I gave you the situation and I said that, I want you to compute the maximum force F that this beam can sustain before it starts to yield. Okay. Okay. And so there is your finite element, or there's your problem. Okay. And so there's a few ways you can go about this, right? And so I think the first way that I think comes to mind, especially in this class, is that we can simulate this in ANSYS. Okay. And so we would take this beam, we would produce a CAD model for this beam, load it up into ANSYS, do the meshing, apply the boundary conditions, maybe do a mesh convergence test, and then we would get our result, okay? And so this will give us one prediction for F, right? Okay. And so in a sense, this is, or, not in a sense, in truth, this is a model for this problem, right? And so we use finite elements, and we made a prediction, and we made a prediction or a computation for F without actually having to construct it, right? That's one way you can go about this problem. Okay? Another way you can go about this problem is you can ask your toddler cousin, right? Okay. And so I actually did this, and so this is based on real data. And so I had back then he was 8 years old, so now he's a lot older. But I went to my cousin and I said that here Jordan, we have a cantilever beam. I want you to tell me what the maximum force F this beam can sustain before it yields. And you know what he told me? At first he told me what, but then I told him it has to be a number. And so he told me 5. And so I said, 5 what? What does 5 mean? And he said, I don't know, 5. And then he went to go play Xbox again. And so, okay. Right, and so we have another prediction here. So we have F is equal to 5, okay? And it's just 5, no units or anything like that. But he's 8, so what do you expect, okay? But and of course, you look at these two options. So you can either do this in finite elements, or you can ask, an 8-year-old, and we get 2 different answers. And obviously the finite element one is going to be a lot more reliable than this one, right? But even though the second example here is really silly, it's still technically a model, right? Because what are the requirements for a model, right? The requirements for a model is that it provides an approximation, or provides a prediction for reality without actually having to go and perform the test, right? And so this satisfies all those criteria, right? Whether this is a good prediction or not, I think, it's pretty clear. But when you're faced with different models like this, we have to have a way scientifically and systematically to say, which models are better or more reliable than others, okay? Because this is an extreme case, right? But you'll come across a lot of different models in your professional life for different things, and there has to be a way to basically say which ones are better than the other ones, right? And the way that we do that is with verification and validation. Okay. All right. Any questions on this? All right, so let's go ahead and define what those terms mean. And so first, let's define verification, okay? And so verification, what this means is this is an assessment of the numerical accuracy of our model. I guess in this case, I'll make it more specific. So we're talking strictly about mathematical models, okay? And so we want to assess the accuracy of the solution relative to what the true solution is to the equations. Okay. And so that's kind of a very long, stuffy definition. And so honestly, I don't remember it like this. And so the way I think about verification is, I ask myself the question, am I solving these equations correctly? Okay. Because when you're talking about, finite elements, right, we know that they're governed at the end of the day by differential equations, right? And so solving differential equations is not a trivial thing. And so, you have to check to make sure that you're actually solving that equation correctly. And so that's what verification hopes to do. Okay. All right. All right, so now let's define validation, okay? And so validation is the assessment of the accuracy of our model. Okay. Relative to the physical observation, relative to the physical observations in nature. Okay. And so with validation, remember, the whole reason why we're constructing a model is that we're trying to emulate a physical situation, right? And so validation, the way that I kind of remember validation is to ask yourself the question, am I solving the right equations? Okay. Or another way you can ask yourself is, am I setting up the simulation correctly? Okay. Right. And so you could be the the most accurate math solver in the world, right? And so you could be a whiz at solving differential equations. All that is meaningless if you're not solving the right equations, right? And so just to give you kind of an extreme example, right? And so let's say that you're interested in solving for the temperature distribution in a CubeSat. Okay. And so you have your CubeSat that's being subjected to radiation from the sun. Okay. And you want to find out what the temperature in that CubeSat is going to be given that thermal loading. Okay. And so it won't do you any good if you take that problem and you solve the structural equations for it, right? Because you're not going to get any temperatures for it at all. Okay. And so you need to be able to choose, what are the best equations to solve what you're looking for. Okay. And to set up the boundary conditions correctly. Okay. All right. And so, these are the two main ways that we assess, how good a finite element code is, right? And so you can imagine that a code has to pass through a lot of these tests with regards to verification and validation, okay? The good news for you guys is that, as a user of ANSYS, which is a commercial software, which has a company behind it that normally charges a lot of money to use their software, they've already done a lot of these tests for you. And so that's kind of what you're paying for. And so a lot of what you're paying for is kind of the confidence and the reliability that your ANSYS results are going to be good. Okay. But notice how I didn't say all of them. Okay. So I said most. Okay? Because even beyond what everything ANSYS does to prove its reliability, there are ways that you can set up a finite element simulation that are not that make it a bad model. Okay. Okay. In other words, it's still possible to set up a simulation that gives you inaccurate or incorrect results. Okay. And so there's ways that you can make sure that you're not doing this. Okay. And we're going to go over what those methods are, in this lecture. And some of this, I do expect you to make part of your final project as well. So it's definitely good to go over it. Okay. All right. Any questions on this?
Yeah, just quick. For the convergence study, would that fall under validation, or would it be like its own form of validation? Because we're not really like trying to see the accuracy of the physical observation, but more of like just the answer.
Yeah, that's a great segue because that's actually what we're going to talk about next. But to quickly answer your question, I consider it a form of verification because the quality of your mesh basically affects how accurately you can solve the equations. Mm-hmm. Yep. Mm-hmm. All right, so let's talk about that then. So so the first thing that you can do to basically make sure that your results are reliable is to perform a mesh convergence test. And this is a form of verification. Nice. And so, at this point in the class, we're all familiar with the notion is that if your mesh is too coarse or if your mesh is poor quality, it's gonna give you an incorrect or an inaccurate result. Okay. Okay. And so another way that you can view that is that if you have poor mesh quality, it's going to mess up how the equations are being solved. Okay, and so one way that you can show that your mesh is adequate enough to solve the equations correctly is to perform a mesh convergence test. Okay. And so just to kind of remind you, the idea of a mesh convergence test is to repeat your simulation or to do your simulation with the exact same boundary conditions. Okay. And so that's really important. And so you can't change the boundary conditions between different tests in a mesh convergence test. Okay. And the only thing that you're going to change is the size of the elements, or how many elements there are in the mesh. Okay. Okay. And so in the end, after you perform all these simulations, you're going to have a plot that looks like the following. Okay. Okay. So normally a mesh convergence test is reported as a line graph or a scatter plot. Okay. And so on the x-axis, we have the number of elements in your mesh. Okay. And on the y-axis, we're going to have our quantity of interest. Okay. And so a lot of times you're going to pick something like the maximum deformation or the maximum stress in your model. Okay. And you're going to see how that evolves as you change the number of elements. Okay. And so a lot of times, you'll see a graph that kind of looks like the following. Okay. Connect the dots, right? And so when you have a small number of elements, you'll usually see that your result changes, as you refine the mesh. Okay. And so that's not good. And so in this area, what we can say is that the equations are not being solved accurately. Okay. Okay. Because ideally, the solution that you get should be independent of your mesh size. Okay. It's only when you get to this region right here. Okay. You could argue that the one I didn't circle that belongs there too, but basically you want to be in a region where when you change the mesh element size, the solution doesn't change. Okay. Okay. And so over in this region, we say that the solution has converged. Okay. And so of course, you want to be in this purple area over here, because that shows you that the numerical errors associated with their mesh are minimized. Okay. Yeah. And so anytime you do any kind of computational work like finite elements, or there's also finite volumes out there, I would argue that a mesh convergence test is almost necessary, because you need to be able to show that your solutions are well converged. Okay. And so that's why, I'm pretty sure I required it on the final project. And so, this is always something that's good to have. And if you're stepping into a job after you graduate and they're going to ask you to do finite elements, I guarantee you that doing a mesh convergence test like this is a very easy way to impress your boss, because that really shows that you really understand finite elements, and you want to make sure that your results are as accurate as possible. Okay. Any questions on this? Okay. All right, so that's mesh convergence testing, and so I'd say that's kind of the primary way that you can verify your results. Okay. And so now let's talk about validation. We're not talking much more about verification because again, ANSYS does a lot of that for you. Okay. And so what when you're using ANSYS, what you're trusting is that they've checked their code for bugs, and they've run all the appropriate benchmark tests out there to make sure that what they're solving for is correct. Okay. And so the only thing you have to do to perform verification in most cases is to just do a mesh convergence test. Okay. All right. So let's talk about validation. Okay. So remember, validation. What we're interested in is if our finite element simulation matches the reality. Okay. Okay. And so in other words, we're checking to make sure that our finite elements actually provides a good model for reality. Okay. And so there's lots of different ways you can perform validation. And it's actually a field in itself. And so if you look into the literature and you search up like validation on Google Scholar, you'll see tons and tons of papers show up. Actually, if you search validation, probably you'll see a lot of other kinds of papers there. But if you search like finite element validation, you'll see tons and tons of papers show up. Okay. Because there's lots of different ways to do it. Okay. And so I'm gonna basically introduce to you, some of the more common methods, and we'll go from, I would say, the best, and we'll go down from there. Okay. And so the best thing that you can do to validate your code is to run what's called a validation experiment. Okay. Okay. And so the idea with the validation experiment is that you're going to set up a physical experiment or a physical test. Okay. And the parameters of that physical test should match exactly what you're going to put into the finite element program. Okay. And so this means that you're going to use the same geometry, you're going to use and the same boundary conditions. Okay. Okay. And so basically, you're going to be performing the exact same, situation in two different mediums. Okay. So one is going to be in the physical world, the other one's going to be in the digital world. Okay. And so ideally, what you should get is both the physical experiment and the finite element simulation should give you the exact same results. Okay. And so let me give you an example of how this would be set up in practice. Okay. So let's say that we have a cantilever beam, which is my favorite example ever, just because it's easy to draw. Okay. And we're going to set it up in two different places. Okay. And so on the one hand, we have a physical experiment in the lab. And then let's say that we set up the exact same situation in ANSYS. Okay. All right. And so in both situations, we're going to apply a force on the end. Okay. And then we're going to run it and see how it goes. Okay. And so in the lab, because this is kind of physically right in front of you, you can perform measurements, in the lab. Okay. And so one thing that you might want to measure is, you can measure how much the deformation is going to be at a point like here. Okay. Another thing you can do is you can use, let's say a force meter, and you can basically strap a force meter onto your beam, and you can use that to measure, maybe something like the stresses in that location. Okay. And on the other side, finite elements, of course, we're going to go through the whole process. And so we're going to apply a mesh. Okay. We're going to apply our mesh. We're going to apply our boundary conditions digitally, and we're going to run the simulation, and we're going to measure the exact same things in the exact same places. Okay. And so let's say that we look at our simulation results and we find out what the deformation is right here. Okay. And so you can just read that off of the ANSYS results, just as we normally have. Okay. And you can also use those same ANSYS results to compute the stresses. Okay. All right. And so ideally, these two should match, right? So the deformation here and deformation here, those should be the same. Okay. The stress here should be exactly the same. Okay. And if they are the same, then that's good. That means your finite element results are validated and they're reliable. Okay. But if they're not the same, you're going to have to check something in your finite element simulation. Okay. And in a situation where they're not the same, it's always going to be your finite element simulations result. Okay. Because Mother Nature is not going to lie to you, and so Mother Nature is not going to get it wrong. And so if you take a cantilever beam, you apply a force, it's going to deform as Mother Nature describes it. Okay. And so don't blame Mother Nature when your validation test goes wrong, okay? Because it's probably your fault. Okay? One of my colleagues in grad school was frustrated in his validation test, and he was getting mad at that they weren't matching. And I said, don't blame Mother Nature, man. I think you just didn't set it up correctly. Okay. Any questions on this? Okay. All right. And so this is the gold standard here. And so, if you can perform a validation test to make sure that your results are accurate, then there's no disputing it at all, right? So there's no disputing whether your results are accurate or not. Okay. But at the same time, this is not something that you're going to do in most of your cases, because the whole point of running a finite element simulation is to avoid doing a physical test to begin with, right? And so most of the time you're not going to be doing this, but these do exist, okay? And so remember that I told you that ANSYS does a lot of this validation for you, okay? And so, even before purchasing the software, ANSYS has performed a ton of tests like these, to make sure that their code can accurately represent these situations. Okay. Of course, they're not going to do every single situation out there. That would be impractical. But they've done enough of like some really key benchmark tests, and a lot of other fringe cases to basically show that their code is well validated. Okay. And so, even though it's true that, most of the time when you use finite elements, you're going to be using a situation, or you're going to be simulating a situation that, ANSYS probably hasn't tested before. But, the fact that ANSYS has done such thorough testing on their software, you can have faith that, it is well validated, even if it may not be for your exact situation. Okay. All right. And so another, I would say, more common way to perform validation, especially in some of the more niche areas of research nowadays, is to compare with published data. Okay. And so, the way to go about this validation is to, scour the literature, okay? And you're going to look up some papers that have performed some kind of experimental tests. Okay. And a lot of times you want to find an experiment that's somewhat similar to the situation that you want to, that you want to simulate. Okay. And so in those papers, the nice thing about those papers is that they have to be very descriptive on how they set up their experimental tests or how they obtain their data. Okay. What you're going to want to do is you're going to want to replicate that exact situation in finite element form. Okay. All right. And so when you run your simulations, in this case, you should be able to recreate all of the published data that's out there. Okay. Okay. And so whatever data that they have in their paper, from their experimental results, you should be able to recreate that data. Okay. And so, this is a really, convenient way to do this, because it lets you, as kind of the user of the software, perform validation without actually having to perform a physical test. Okay. Actually, one of my grad students is working on something like this right now, actually. So, what we're trying to do is we're trying to simulate the flow of blood through a blood pump, basically, okay, through a centrifugal blood pump. And the FDA has actually performed a lot of experiments to quantify the flow through a sampled blood pump. Okay? And so what he's going to do is that he's going to take that blood pump, simulate it within ANSYS, and see if we can recreate the exact same data that the FDA produced. Okay. And so if we do that, then that's going to be a great thing, because then that tells us that we can use simulations to predict or compute the flow through these blood pumps. Okay. And so this is really popular in research, because it basically lets someone else do the experiment, and then you can just focus on the computations. Okay. All right. Yeah. So if you can do this, this is always a good thing. But but kind of the same thing with the last topic that we just went over. As a simple user of the software, this is not something that you're going to be expected to do. Okay. And so if you go out and work for a company, you're not going to be asked to validate against published data, okay? Especially if you're using something like ANSYS. Okay. All right. And so why am I telling you this then, right? And so why do we go through the concept of a validation experiment, and why are we talking about validating against experimental data? Okay, because unless a lot of you guys end up working for ANSYS or you end up working for a developer, probably you're not going to be doing these things. Okay, but they are really important to know. Okay, because a lot of you are probably going to exit this class and you might use a software that's not ANSYS. Okay. And so we live in kind of a very interesting world in terms of software development. Okay. And so there's a lot of projects that are called open source. And so are you guys familiar with what open source means? Yeah. So open source basically means that people develop code and then they put it out for free on the internet for people to use. Okay. And there's open source everything nowadays, but there's actually also a very active and very vibrant community of open source finite element developers. Okay, and so a lot of people, they write finite element codes and then they put it out there for people to use for free, which is great. Okay. Okay. And so a lot of times these are really good because if you look at the price of ANSYS, of what you need to pay to use it versus just getting something for free from someone, getting something for free is really nice when you see ANSYS with thousands and thousands of dollars. But you have to be careful because a lot of these open source codes, and there's some that are really good out there that have strong teams, but a lot of times these open source codes that you find are just one dude, one person in their garage just coding for fun and just putting their code on the internet. Okay, and so these open source finite element codes, I guarantee you, have not been validated against the plethora of tests that are out there that ANSYS has done. Okay. And so it's tempting to see that we have a code out there that's free and you can use it to apply to your problems and you don't have to worry about the numerical limits and ANSYS and stuff. Okay. The only thing I would say is just be careful because a lot of these codes, they may look, of course the developer is always going to make them look really shiny, but do your due diligence, and so perform some validations, and so try to find some published data out there, or even better, I know a lot of you are in like the student projects. If you run some physical tests on certain geometries on certain parts of your vehicle or whatever you're designing, try to see if you can replicate those that data in finite elements, with these open source codes before you actually start using it for design and things like that. Okay, and so I bring up these last two things of validation just to in case you're going to use codes like that. Okay, because I've used a lot of codes like these too, and they're great. The fact that people are writing these super complex codes and putting it out there for free is awesome. But just be a little bit careful and do your due diligence. And it's not that any developer out there is maliciously trying to put out bad code for people to use, but they are very limited in their resources. And maybe they're designing their code for something that's not exactly the same of what you're going to use it for. Okay. And so the amount of use cases out there is almost infinite. So it's impossible for just one person or a group of people to cover all those things. Okay? And so do some validation if you can, and I trust me, it'll make you feel a lot better of using their code as well. Okay. All right. Any questions on this? Okay. All right. And so what if you have none of the above, right? And so let's say that you can't run a validation experiment and you can't check against some published data. And so is there anything else that you can do to validate or check your results. Okay? And so there is something, okay? And so that something is what I like to call a simplified model, okay? And so this is not, I call this validation, but it's not validation in the true sense because, we're not comparing against physical measurements, but this is more of like providing a sanity check for your finite element simulations, okay? Okay. Because when you're using a software like ANSYS, it's really easy and it gets really tempting to kind of take everything that ANSYS gives you at face value and say, yes, ANSYS, of course, the deformation is 10 millimeters. Of course it is, but you never want to be and this is true for your personal relationships too. You never want to be in a situation where you're getting all your information from just one source or all of your advice from one source and then trusting it at face value, right? And so, so a good thing to do, and I want you to do this for your final project too, is to check your finite element results against another type of calculation. Okay. And so in the past, I've been a little bit lax on this. And so, when I say simplified model, some people think that it's, I want you to run a finite element simulation on a simplified version of your geometry. And so that's not what I want. Okay. And so what I want is I want you to perform a different calculation besides finite elements on your problem that can let you check your results. Okay. All right. And so let's do a quick example. Okay. And so, let's say that we have a bar. Okay. And let's say that we're pulling on this bar with some tension. Okay. And then in addition to that bar, let's just say that we have the bar. Okay. All right. And so, of course, we have a 1D situation like this. We can simulate this in ANSYS, no problem. Okay. But I want you to check your results against something else. Okay. And so when I say to check your results, I want you to solve the same problem, but using a different method. Okay. And so some methods that you can use, say, the direct stiffness method. Okay. Even though the direct stiffness method is technically finite elements, but it's not the same method that ANSYS uses. Okay. And so it would be good to use direct stiffness to verify your results or to validate the results. Okay. Okay. Another way you can check your results is you can have an analytical equation. Okay. And so we can basically directly solve the differential equation for this problem. And since, and I picked this one very carefully because it's 1D. Okay. And so for 1D, bar in tension like this, we can solve this differential equation for the displacements. Okay. And so that's another thing that you can do. Okay. Right. Or another thing that you can do, what also counts as a simplified model specifically for the project, is you can check against some physical observations. Okay. So I know a lot of you are doing your final project, based on either your senior design project or one of the student projects here on the campus. Okay. And so if you have some data, either from past competitions or past years, where you kind of measured some kind of deformation in the in a similar part, you can use that data to validate your results. Okay. And so the whole point of this is, I just want you to check your answers against something, so you're not just relying on answers. Yeah.
Let's say the analytical equation was pretty difficult to solve.
Mhm.
Could we use like a numerical method to solve it?
Sure. Yep. Yep. So as long as it's not ANSYS, then it's anything is fine for this. Yeah. Mhm. Yeah. So when I asked you to do a simplified model in your final project, this is what I mean. So, another way you can think of it is, imagine you're trying to perform this analysis or do this design work, and you had no idea what ANSYS is, right? And so think about how would you approach this problem, or how would you compute your solution without using ANSYS, and then use that method to check your results, right? And so I know in a lot of your proposals, you've a lot of people have already thought up some simplified models, which is great. Okay. A simplified model can be something as simple as just an algebraic expression. And so, I saw this in a couple proposals where you said that, I can validate the stress by just computing, maybe the tension over the area, right? Right. And so let's say that, we're trying to validate the stress in this area right here. Okay. And so that works too, right? And so, it might look like a very simple algebraic expression, but it's a computation that you can do that's not ANSYS, that you can use to check your results. Okay. Because what you can do is you can take, this stress and then compare it to the stress that you actually get in ANSYS, and you should hopefully see that they're the same. Okay. All right. And so, the definition for simplified model, I know is very vague and very broad, but it can really be almost anything. All right. Any questions on this?
Yeah, so if it's like Kachavi said too complicated, would we be able to kind of like model it as like 1D?
Yeah.
Or
Yep. Yeah, so I know probably a lot of you will have to do that for your projects, because I know your geometries are probably going to be pretty complex. And so you might have to simplify it, or maybe just take a small portion of that geometry in order to do a hand calculation like this. Yeah, and so that's totally fine. And so I think in past years when I've run this project, the most questions I've gotten on this project is about the simplified model, because a lot of it is gonna require you to kind of think a little bit outside the box of how can I do a hand calculation on this? How can I simplify this to do a hand calculation? And I know that's not easy, especially with with how complex a lot of your situations are. So don't be afraid to reach out. And so if you're having trouble thinking of a simplified model, then let's talk about it. Come to office hours, shoot me an email, and I'd be happy to help you out. Okay.
I have a question about
Yeah.
the simplified model.
Yeah.
So for different cross-section areas, if like we consider like a beam,
Mhm.
we get like different eyes, right? Is there any
Yep.
source we can just like, just find out like different value of eyes for different cross sections? Like,
Yeah. So, and I think that's a great question considering what your project is. And, so I'd say there's a couple ways you can do that. And so if you have kind of a very irregular, a very complex cross section, I think you can kind of approximate it as a simpler shape. And so I think for you, using like a cylindrical or a circular cross section, I think makes a lot of sense. And then you can look up those values online as well. And so if you assume that it's basically a circle, and you can compute the moment of inertia of that circle, and then you can plug it into an analytical expression like this. Yeah. Mm-hmm. Okay. Any other questions on this stuff?
yeah, what if the simplified model is completely way off, even though they did correct.
And so the question was, what if the answer to your simplified model is way off? And honestly, I think that's probably going to be the case for a lot of you guys. And so, don't fret. And so, because for a lot of situations, especially with how complex some of your guys are, it's going to be really, really hard to come up with a good simplified model, to the point where, your simplified model probably is not a good representation of your geometry. But that's okay. And so, I'm not going to grade you whether or not you're going to match your simplified model. I just want you to think about it and come up with a good one, and and to kind of show that, or to kind of go through the exercise of of checking your results. And that's kind of the important thing for me. Yeah. But on the job, if you go work for a company, don't say that, all my results don't match, but Professor Tran said it's okay. So it's not okay in reality. It's only okay for this project, just because, we're pretty limited in what we can do here with ANSYS. Okay. All right. And so the last thought that I'll leave you with is kind of a broad statement of why verification and validation is important. Okay. And so I would say kind of the biggest reason why they're important is, because without verification and validation, your finite element simulations are effectively useless. Okay. Maybe I shouldn't say useless, because it's because you can still do some computer animations, and so we won't say useless. Maybe we'll say it's bad Pixar. Okay. So you can do some computer animations, but it's not really useful for engineering work. Okay. Because in order to use finite elements to perform engineering, we really rely on the fact that what we get from finite elements is an accurate depiction of reality. Okay. Because in engineering, we're eventually going to be building a lot of the structures that we're simulating. Okay. And we want to make sure that our FEA is going to predict reality to some degree of accuracy. Okay. Okay. And so that's kind of the big overarching reason why V and V is important. Okay. The other kind of more practical reason why it's important for you guys in particular is that what you'll find is that if you go out in industry and you perform any kind of finite element work, your biggest struggle is not going to be in the simulations. Okay. Your biggest struggle is going to be in convincing other people that your simulations are actually legit and reliable. Okay. Okay. Especially as a young engineer that just came out of school, right? And so, people are going to expect you to be able to do these kinds of things, right? And so the way that you convince people that your FEA is reliable is to perform these verifications and validations, right? So perform a mesh convergence test, check your results against a simplified model, right? Validate against some experimental data if you can, right? Validate against some internal data if you can, right? And so the more V and V that you do, it basically adds more credibility. It adds more evidence that your FEA is reliable and accurate. Okay. Okay. And that's important, right? Because you want people to trust that your simulations are reliable. Okay. And this is how you can do it. Okay. And it's also a great way to check too, because if your simulations are not reliable, then these give you the tools, or these give you the methods that you can use to fix your simulations. Okay. Okay. Oh, nice. Yeah. Thanks, Isaac. Okay. All right. Any final questions before we wrap it up for today? Okay, all right, and so that's all we got time for. And so next time we meet on Thursday will be the exam. And so remember to come in person, because there's going to be no online component for the exam. Okay, and so make sure you bring your writing utensil, bring your calculator, and bring your cheat sheet. Okay, all right, and so we'll be signing off here for today. So hope everyone enjoys the rest of their evening. Thank you again for coming to the lecture, and I will see you all in person on Thursday.
Thank you, Dr. Tran. Bye.
Thank you.
Thank you, Professor.
Thanks, guys.
Thanks, Dr. Jen. We'll see you on Thursday.
Yep, see you Thursday.
Thanks again. See you Thursday.
Yep.
Yeah.
Yeah, I know. It's not perfect. It's not designed for this.
So, like, can you explain what I have to do in 5, 6, and 7?
Yeah.
So, like, what I have to do?
Oh, so for problem 5, and so when we set the optimization, we had a few outputs, right? And so the outputs were things like the deformation and things like that.
Maximum stress.
Right. And so yeah, you can change this to the stress, right?
No, this is equivalent distress.
Oh yes, yes.
So these were 2 outputs. So like I can add the strength.
Yes. Yes.
So like this will be done for the problem.
Yes. Yep. Mhm.
And shoot. Close it.
So problem 6 was
Sorry. In loading.
uh-huh.
And changing the loading.
Oh yeah. Mhm.
So like we already have like added 1 loading.
Mhm.
So like you want us to add another loading, or we can change the magnitude of.
You can change. Don't just change the magnitude. I would
Oh,
just
sorry,
change
the
the
direction.
direction. Yeah, either change the direction or add another one. Yeah, and then redo the optimization.
The number of inputs. So number of inputs are our.
Those are your design parameters. And so, because right now you have the radius of the fillet, and then also the thickness of something. And so you can add one more input. And so if you open up and design modeler, just add another P for one of the dimensions. So you can,
Okay, sorry. So like in problem 5, I already have added strength,
yeah.
and I can continue with the same.
Yeah.
And for the loading.
Yeah, you can do that.
And I can continue the same with the number of inputs, right?
Yeah.
I don't need to,
You don't have to go back to the default settings for that.
Got it. Thank you.
Yeah. Mhm. Sure.
First one was, I did one of the surgery.
Mhm.
Was there any talk about the midterm or like the project, or was it just a recap of the rotational?
Yeah, it was. I haven't graded the midterm yet, and
Okay.
so and I think mostly everyone's picked a project at this point. I think you're good to go. And so you have
Okay,
your,
yeah,
so,
group of 3, right?
Yeah.
3 max, right?
yeah, 3
Okay,
months.
cool.
And so yeah, and so I'll probably I think I should be able to grade the midterms by tomorrow.
Okay.
I don't know if I can give you guys I can give you the score, but I can't give you
No,
the.
I'm
the
okay. No, I
scan.
just wondered if I missed anything besides.
Oh, yeah, no big announcements. It's just, project is out there and just kind of get started on it because it is a lot of research to do.
Okay,
So,
okay.
yeah.
All right, cool. Thank you.
Yeah. Mhm.